Hi, my name is Bhavya Balu. I'm a PhD student with Professor Aditya Kher, working at Carnegie Mellon University. And today I'm going to be talking about the dynamic double layer force between charged surfaces, which is the electric force between two charged surfaces in an electrolyte. So charged surfaces in electrolyte have a lot of different applications. And so the standard example is an electrochemical cell where there's a solid electrode in contact with an electrolyte. You can also think of colloidal systems where you have charged colloidal particles being suspended in an electrolyte medium. In colloidal systems, the force of interaction between two colloidal particles determines the stability of these colloidal suspensions. So it's important to understand the nature of the force between colloidal particles. On the other hand, you can also think of biological systems such as neurons, where you have charged membranes in contact with electrolytes. Here, the membrane is soft and can be deformed by these electrical forces. Additionally, the charge on these membranes are not necessarily constant, and so these systems are not necessarily in equilibrium. You can go somewhere between these two extremes of a hard electrode and a soft membrane, things like soft electrodes, where you have things like wearable technologies and probes that are made to be biocompatible. You have soft, deformable surfaces that hold electric charge. Now, while designing these systems, you want to be aware of what kind of electrical forces are going to be generated to make design choices. One thing I want to point out about all these systems is that the actual electric force, whether it's in colloidal systems or in biological systems, is kind of small. So the force per unit area is about a few pascals. And so these have been really hard to measure for a really long time. But recent advances in experimental methods have allowed the measurement of these electrical forces very precisely. So a couple of groups have done this where they measure the electric force between two charged surfaces in an electrolyte through a modified surface force apparatus, where the surfaces of this apparatus are now electrified and they're able to apply a potential difference across them. This potential difference or voltage can be a function of time, and so they're able to measure the dynamic or time-dependent force between these two charged surfaces in an electrolyte medium. Now, this is really cool, but the theory that exists for these surface charges only describe equilibrium, so they don't really account for the time-dependent force between these two surfaces. So that's where we come in, and our goal here has been to develop a dynamic surface force theory, which basically describes the time-dependent force between these two charged surfaces in an electrolyte medium. So to do this, I want to first understand what happens in between in the electrolyte when you have charged surfaces near it, and think of the physical origin of what the force, where the force comes from, and then we'll go with the mathematical description of the system. So to study the force between charged surfaces, the model system that I'm using is this electrochemical cell with parallel electrodes and an electrolyte in between. Here, we want to figure out what the force evolution looks like between these two electrodes. So this is kind of hard to imagine intuitively, so I'm going to walk through it step by step. So when there's no applied voltage, there's no charge on these surfaces, and the ions are uniformly distributed within the electrolyte. And now we want to look at what happens when you apply a voltage. So a couple of things immediately happen. The electrodes get charged. So now you have your two charged surfaces. Now the electrolyte in between, the ions in the electrolyte, still really haven't had a time to respond to the applied voltage, and so they're still uniformly distributed at this point. So we have our two charged surfaces, which are essentially interacting through a dielectric medium. And so the force of interaction between these two surfaces in the initial state is basically the dielectric force. Now, as the ions in the electrolyte respond to the applied voltage, they move towards oppositely charged electrodes, and they form what are these diffuse layers of charge in front of each electrode. These diffuse layers essentially screen the applied voltage from the bulk of the cell, and in doing so, they greatly reduce the force of interaction between these two electrodes. Because you can imagine, now they're not just interacting through a dielectric medium, but they have these complex, they have these charged structures in front of the electrode that greatly diminish the interaction force. Now, the final value of this force has also been developed a while ago, and this equilibrium force is given by DLVO theory, which is a classical theory in colloidal science. But our goal here was to figure out and quantify what happens in between these two states, where or how the force evolves from this initial dielectric force to this final double layer DLVO theory force. So before we go there, let's look at what really causes the force, like physically. So let's take a closer look at one of these electrodes. If you look at the negative electrode, it has a diffuse layer of positive charges in front of it. Now, in this diffuse layer of charge, there's a greater number of ions. And so this causes an increase in the osmotic pressure in this diffuse layer. And this increased osmotic pressure in turn causes a net force on the surface. Additionally, across this diffuse layer, there's a potential gradient. That is, the electric potential drops from being whatever is the applied voltage at the surface to just zero in the bulk. And so most of this transition occurs in this diffuse layer. And so you have a sharp electric potential gradient. And this contributes to the total force through the Maxwell stresses. One thing I want to point out is that the force depends on the square of the electric potential gradient. So the force is inherently nonlinear on the electric potential gradient. Now, the other thing is that the actual ion distribution that we are interested in is out of equilibrium. So we're not considering the equilibrium ion distribution. So the ions are not just in a Boltzmann distributed way. So what we need to do is figure out how the ions are actually distributed as a function of time, and also how the electric potential is distributed as a function of time, and then figure out what the total force would look like as a function of time. So to figure out what the ion distribution looks like, we go to our ion transport model, which is basically the Poisson-Nernst-Planck equation with our species balances and electric potential balance. Here, the species balances are conservation equations for the ion concentrations N plus and N minus. On the left-hand side, we have a time-dependent term, which is how these ion concentrations vary with time. And these are balanced by the fluxes. Here, D plus and D minus are the diffusion coefficients of the ions. The first flux comes from diffusion, which is basically due to a concentration gradient. And then the second contribution to the flux is an electric migration flux, which is because of the charge nature of these species, they move under an electric potential gradient. We also have an electric potential balance, which is where the electric potential is balanced against the charge density in the system. Here, phi is the electric potential. Now we can solve this system of equations in the limit of weak applied voltages. That is, the applied voltage is smaller than the thermal voltage scale. And using this, we're able to derive an asymptotic approximation to the ion distributions and electric potential in the system. And using that, we're then able to derive what the force looks like as a function of time, an approximation for what the force looks like in the system. Now, without going into too much more detail, I want to start talking about the main result of this calculation. So to do that, let's look at a plot of the dynamic force on the y-axis with respect to time on the x-axis. Here, the dynamic force is the transient force subtracted by the equilibrium value. So I've removed the equilibrium contribution to the force, and this is just the transients. This is a log linear plot, and you can see that the dynamic force seems to have two sort of straight line evolutions. So a straight line in a log linear plot indicates an exponential decay. So this basically means that the dynamic force is composed of two exponential decays. This is also reflected in the expression that we derive, which are written up here, where you can see the two exponential functions that contribute to the total dynamic force. These two exponential decays or evolutions have two different timescales. So let's take a closer look at what these timescales are and what they can tell us about the system. So the initial evolution of the dynamic force follows this RC timescale. The RC timescale is a characteristic timescale for the charging of a typical electrochemical system. This depends on the diffuse layer thickness, kappa inverse, and also the salt diffusion coefficient. But at longer times, we see that there's a longer, slower decay on the diffusion timescale, tau d. Here, the diffusion timescale only depends on the salt diffusion coefficient, dA. Now, what we say is that from an experimental measurement of the dynamic force with respect to time, we're able to get these two different timescales. And from these two different timescales, we can extract physical properties of the electrolyte, such as the salt diffusion coefficient. So now this is the gist of the theory that we developed to describe the dynamic force evolution as a function of time. And we do this for a suddenly applied voltage. So let's take a step back and look at how this actually compares to experimental results that I mentioned previously. So once again, we have our theory, which predicts an exponential decay along times, and we consider this model electrochemical cell under a suddenly applied voltage, and we're looking at the force between these two electrodes. An equivalent experiment was done by Tavoni et al. A couple of years ago, where they consider a surface force apparatus, a modified surface force apparatus, and they suddenly apply a voltage across these two surfaces and study the evolution of the system. So the good thing is that the evolution of force that is experimentally observed does follow an exponential decay. However, there's still some big gaps between our theory and the experiments. So the main issue is that the time scale that are observed in experiments are much larger than that obtained by our theory. It's in our theory for the given experimental conditions, the timescale predicted is about a few microseconds, but the actual experimental timescale is in the order of seconds, and so this is quite a big discrepancy. And so I just want to take a minute to put forth some of the reasons for this. So again, we consider a model electrochemical cell, and the main difference between our system and their the experimental system is that in our cell, we consider one-dimensional transport just between these two electrodes, and the ion transport's only perpendicular to the electrodes. In the experimental system, it's really not just ion transport between these two surfaces, but rather ions move from this bulk reservoir surrounding the two surfaces into the gap between the two surfaces. So there is also some component of tangential transport parallel to the electrodes, which is in fact what causes this much larger time scale. So there's definitely room for adding multiple dimensional transport to our theory. And so I just want to, but this is still a good first step towards figuring out the dynamics of the surface force in electrolyte. Just to conclude, we developed a new theory for the dynamic electrical double layer force between charged surfaces and electrolyte under time-dependent voltages. And with this, I'd like to thank you all for listening and also thank my funding sources. If you have any questions or comments, please feel free to reach out to me at my email. Thank you.